4.6, electronegativity and bond polarity. Notice this electronegative chart here. We're going to use this to determine our electronegativity and bond polarity. So it's good to dog-ear this in your book. So what electronegativity is, it's a value. And it's a value of an element that indicates the attraction of an atom for the shared electrons in a bond. It increases from left to right going across a period on the periodic table. For the nonmetals, it's high and it's low for the metals, and in the nonmetal section, the fluorine is the highest. Notice as we look at this table, we're not even talking about the noble gas group. So make sure that when you look at this, you notice that, okay, as we go closer over here to fluorine in this period, that the value, which is the 4.0, is higher than any of these other values here. And the electronegativity gets smaller as you go down the periodic table. So we could compare to see, if I were to say, well, which of these elements is going to be more electronegative, fluorine or phosphorus? Well, we look at the position on the periodic table and we see that obviously fluorine is. So anything that is closer to fluorine is going to be having more electronegativity, which is more of the attraction of the electrons to be held within its shell. So I could compare sulfur to selenium. In that case, sulfur is going to have a higher electronegativity than selenium. Not by much, don't get me wrong, but that's a generalization, and you can see differences over here. But if we're just going to compare from here to here, that's a nice generalization. Well, this all has to do with covalent bonding, because covalent bonding, we learned in the last section, was all about sharing of electrons. Well, the only thing is that some sharing is totally equal, but some sharing is not. You know, like maybe you have a brother or sister that expects you to share all of your stuff with them, and yet they don't share with you. Kind of unequal sharing. Or let's say you have a wonderful twin that is willing to share everything with you, and you with that person, well, then that's going to be equal sharing. Well, equal sharing of these electrons within the bond has specific names. If it's unequal sharing, they're going to call it polar, because it's going to act charged. If it is equal sharing, then it is going to be called nonpolar. So let's go ahead and look at this chemically. In the nonpolar covalent bond of H2, electrons are shared equally. In the polar covalent bond of HCl, the electrons are shared unequally. And so they designate this here. Look at the HCl. Notice the electron that hydrogen was kind of willing to share, it's going to be spending a little bit more time over here around the chlorine side, and that's what's designated here by this larger ball here. Whereas over here with hydrogen, the sphere of where the electrons are hanging out is about the same size. Whereas here the sphere the chlorine is a much bigger area and representative. But rather than having to draw these out, we represent these with this symbol. Because electrons are negatively charged, and because the electrons are going to hang out a little bit more around chlorine than hydrogen, then we'll put this partial negative sign above chlorine. And on hydrogen, because the electrons aren't hanging out there as much, then we're going to call it partially positive. Well, here we go. A nonpolar covalent bond. First of all, it's covalent because it's going to occur between nonmetals. And nonpolar has an equal or almost equal sharing of electrons. There's a very small electronegativity difference. So let's look and see. Let's say we had 2 atoms of our nitrogen to make our nitrogen molecule. Well, when you look up on the table right back here at nitrogen, nitrogen's electronegative value is 3.0. Well, one of the nitrogens is 3.0, the other one is 3.0, so the absolute value, when you take the absolute value of 3, take away 3, is 0, then there is no difference there in electronegativity, so we're going to call it nonpolar covalence. When we have a chlorine to bromide bond, chlorine, when you look at chlorine's electronegativity, it's 3.0, whereas the bromide is 2.8. So when you subtract that, that difference is 0.2. And you go, wait, that is a difference, it's not 0. Yeah, but it's got to be enough to actually make a difference, which we'll talk about that in a second. So it's still considered nonpolar covalent. Why? Because it doesn't act polar. When we look at the hydrogen in silicon, our hydrogen's value is 2.1, and our silicon's value is 1.8. When we subtract those, that's 0.3 difference. Still not enough to act polar, so we're going to consider it nonpolar. So the question kind of is, then, what is enough to make it act polar? Well, look at here. A polar covalent bond, yes, it's still a covalent bond when it's between non-metal atoms, but it's an unequal sharing of electrons that has unequal enough to actually make a difference. So if something is 0.5 or more, it is a big enough difference to be considered polar. And of course it's polar covalent because it's a covalent bond. If something is 0.4 difference, it is not enough to be considered polar. So the difference is that if it is 0.5 or more in the electronegative difference between the 2 atoms, it is considered polar, and it's going to act polar. So when we look at a chlorine to carbon bond, and you look at those values, we get the difference is 0.5, yes, polar. If we look at an oxygen to sulfur bond, the 3.5 minus 2.5, 1, obviously polar covalent. Well, let's look at the difference with ionic bonds. Now, we predicted that the polar and nonpolar would be talking about covalent bonds. Why? Mostly because I said it was between 2 nonmetals. But let's just look and see how this verifies what we're talking about with ionic bonds and covalent bonds. Ionic bonds, remember, are between metals and nonmetals, and the electrons are transferred rather than shared. Well, so this has such a huge electronegative difference that is what is going to make the ionic bond such a strong attraction, and it's going to make the ionic bonding of ionic compounds to have such a high melting point. So if we look at the electronegative difference between a chlorine and potassium, we look at that, and that is 2.2. Well, first of all, we would also see that potassium is a metal, and you might go, well, why didn't they write potassium first and chlorine? That's a really good question. I would have done that. All right, so then sodium and nitrogen. When you look at that, sodium's a metal. We would have predicted that, yes, it would have been ionic bond. So when we subtract that, we are going to get 2.1. Yes, we already knew it was an ionic bond. Now then, sulfur and cesium. When you subtract those electronegative differences, you get 1.8, and you get that ionic bond. So here's another number that is not as important to me as the polar versus nonpolar, but let's say the electronegative difference is so huge, and that huge number is 1.8 or more, then they classify that as an ionic bond. Usually in generalization, we have just learned in a different way that an ionic bond is going to consist of a metal and a nonmetal. Well, this is just another way to look at it. When you have a metal and a nonmetal, Usually the electronegative difference is usually 1.8 or more. So you can look at our different molecules and predict what kind of bond type it is. And of course, in doing this, you would need to remember to use the electronegative chart. So a hydrogen to hydrogen, well, I don't care what value hydrogen is, but if you have the same value, it's going to be 0, so of course it's nonpolar covalent. Ditto for the chlorine. Let's look at HBr. Well, HBr, we have hydrogen. Yes, it is over on the metal side, but they quite often put the hydrogen more in the middle, and hydrogen is a non-metal. It's a gas, so you look at that difference, and it's 0.7, which goes to verify that it is covalent, but it is polar because it is 0.5 or greater. Notice on this that because the bromium ion here, the bromide ion here, has the stronger value, the 2.8, that's why they're going to put the partially negative sign there, and the hydrogen has the partially positive. HCl, this chlorine has the electronegative value of 3.0, hydrogen's value is 2.1. We subtract that, yes, it is 0.5 or greater. It is polar covalent, just like what we would predict. But let's look at this ionic compound. Why do we know it's ionic? Well, because it's a metal first. But let's verify this to see if its value is greater than 1.8. Okay? Well, sodium. When we look up its value, it is 3.0. Chlorine's is 0.9. You subtract it, it is 2.1. Yes, it is greater than 1.8. It is ionic, but we knew it was ionic. Notice the difference in these symbols here up here, though. When it's sharing, then we have this partial positive, partial negative. But with our sodium here, it doesn't share. It gives up and loses that electron. Hence, that's why it has the positive charge. So with ionic compounds, these are going to not have that partial charge there. It's not going to have this partial sign there. It's going to be a real charge. All right, press pause and see if you can figure out, are these nonpolar, polar, or ionic? Well, in order to do it, you're going to have to look at the electronegative table in order to calculate these values. So let's do that. Our potassium difference, our potassium, 0.8. Our nitrogen is 3. So 3 minus 0.8 is a 2.2 difference. So we know that that is ionic. We would know it was ionic anyway because potassium's a metal. Let's look at nitrogen and oxygen. Okay, oxygen is 3.5, nitrogen is 3.0. So it's 0.5 difference. And you go, well, what if I had subtracted the nitrogen and go nitrogen minus oxygen's value? It's okay. It's the absolute value. So just put the bigger number first, subtract the smaller number from it. So it is greater, that it is 0.5 or greater. So yes, it is going to be polar covalent. Chlorine to chlorine, 0, so it is nonpolar covalent. HCl, hydrogen's 2.1, chlorine is 3.0. You do the math, and that's 0.9, so it is considered polar covalent.